So in order to do that, of course, because these very intense X-ray pulses turn the molecule into a plasma, you have to capture the diffraction pattern before the atoms have a chance to move. And then you have to have many identical molecules, which should be possible, and you have to collect information from these, and you have to then analyze all this data to do the reconstruction. And in fact, there is a talk also on Thursday by White Elser, I believe, who will talk about how to deal with the data reduction problem in this situation. Now, if you could align those molecules, then the situation would be easier and you wouldn't have to do that many. Or on the other hand, if it turns out that the molecule is floppy and it can take on many different orientations, then of course the problem becomes more difficult. 10 years ago already, Janos Kirz group has made calculations to indicate that if you hit a lysozyme molecule with a free electron laser pulse, it will take only a few tens of femtoseconds before the molecule flies apart, and that sets the time scale during which you have to collect the information. So the scheme that is being planned at the X-ray free electron lasers is that you inject identical molecules one after the other so as to then intersect the free electron laser pulse. You collect the diffraction pattern on a fast CCD detector, and after you have taken maybe 1 million of these diffraction patterns, you are then faced with sorting out which of these corresponds to a given orientation of the molecule. Then you take those, you average them, and then once you have a significant, statistically significant diffraction pattern, you then have to populate reciprocal space with all that information. You have three-dimensional speckles all over that you can then use as the starting point for the phasing of the image to reconstruct the molecular structure. Now, this VUV soft X-ray free electron laser flash that I mentioned to you has been working for some years, has been used toward a proof of principle of this approach, and this is the work of Henry Chapman and collaborators. The idea is to take a microfabricated sample, hit it with a pulse of free electron laser, collect the diffraction pattern, and see whether you were able to collect it fast enough so that it is reconstructible. The object that was picked was a piece of silicon nitride membrane into which some lines were etched in the pattern that is shown. Each of these objects, each of these characters is about a micron in size. And the diffraction pattern from a single pulse of the free electron laser is shown here. And the reconstruction was successful and reproduced quite faithfully the object that was hit. And the comparison is quite good with a transmission electron microscope image. If you then try to hit the same object again, you find something very different because the original object has been heated to 60,000 degrees, so there is nothing left to image. At Lawrence Berkeley Laboratory, we are also planning to build a soft X-ray free electron laser. And the purpose there is to have a, I'm just trying to check to make sure that I don't hold you back from lunch. Our purpose is to build a soft X-ray free electron laser where you have a large enough number of pulses so that you can afford to take multiple images of the same sample if you so desire. In other words, you can be gentle in your hitting the sample because here, as opposed to the X-ray free electron lasers, you have on the order of 100,000 pulses a second. So you have go at 100 kilohertz, and you have variable wavelengths and variable pulse lengths. And that flexibility is going to complement very well what we have at the advanced light source. So in this comparison that you see here, you see that the free electron laser, of course, will be fully spatially and temporally coherent, and it gives a considerably higher coherent power than we have at synchrotron light sources today. And in terms of imaging applications, and of course there will be many other applications, it will make it possible to do flash microscopy in 2 dimensions with or without lenses. We will have to see to what extent lenses will survive in that beam. And in particular, it should be possible to do pump probe or pump flash imaging activities to observe the time dependence of light-activated phenomena, look at dynamics in magnetic spintronics, and to study laser-matter interactions, which is of considerable interest. One can also consider splitting the beam and thereby do stereo flash imaging. But no matter how you do it, you probably will not use 100 kilohertz in this application, but use a relatively smaller number of pulses, because you have to record from each of these pulses in a 2-dimensional fashion. On the other hand, if you have identical samples, then you can do something similar to what is being planned at the hard X-ray free electron lasers, except for the fact that you gain because the signal will be larger from each of these samples. The signal typically goes as the wavelength squared. So if you go to 1/10 of the energy or 10 times longer wavelengths, you get 100 times more signal from each of these. But on the other hand, you have to give up the atomic resolution because your wavelength is now several atoms long. And so what you can get is information about larger objects like viruses and nanoparticles. And with that, I will want to conclude I hope I have convinced you that X-ray microscopes complement other forms of microscopy and have many exciting applications, and this is a very